try to pick up where we left off on Monday. And on Monday, we finished talking about, I think this was the last slide we used on Monday. Is that right? Right there? Where we talked about the ASCII code was the last thing I discussed that there. So again, a lot of this should be review. You should be, in other words, I'm hoping that you've seen this before in your basic digital class, which I happen to be teaching right now as well. So that there, and the book that uses the basic digital did cover all this now. There. Okay, this again is basic review. That there's two voltage levels. That there. This slide is a little bit dated, and the reason I say it's a little bit dated is because traditionally digital electronics were between a high was 5 volts and a low was 0 volts is what we considered. In reality, the range here for a high is about 2.7 volts to 5. This slide shows 3, and 0.7 volts to ground or to 0. And it shouldn't be a surprise if you had a course on transistors that 0.7 happens to be the turn-on voltage for a transistor. So that's really the key, the reason that's the low. Most digital electronics that we see today, including the microprocessor we're using in this lab, are 3.3 volts instead of 5 volts. Traditional has been 5 volts, and it's been 5 volts since 1975 or so, when the first digital transistor family came out. Texas Instruments started putting out was the first one to put out a lot of, the 7400 series started, like I said, in 75, 73, somewhere in that neighborhood. It's been 5 volts until about 4 or 5 years ago, and now I'm starting to see some 2.7 volt devices out there. As electronics get smaller, and in particular digital electronics has gotten smaller and smaller and smaller, there's been an effort to reduce this voltage in order to reduce the size of the components, particularly the capacitors for filtering and things like that, and the gate width. And we're not going to talk too much about that there, but it's the physical characteristics of how these ICs are made that they now require less voltage. So 2.7 volts to 3.3 volts is pretty much a standard today. So, but the key thing here is that you've got a region that is high, in a region that's a logic 0. Now, when we talk about our signals later on with the microprocessor, we'll use the term active high and active low. Have you ever heard that term before, active high or active low? An active low means that you turn on a device. Active high means that, in other words, you take it low in order to turn on that device, or you interpret a low as being a valid signal. So, for example, if you have a sensor, I don't know if they've got them here. I haven't ran across them out there, but it's very common in many countries at a traffic light, where they have a right turn lane. In the U.S. would be a left turn lane, where you have to have the arrow to cross the other traffic and block traffic. So they would have a sensor under the pavement to sense the weight of the car and turn on the turn signal light if there's a car there. If not, skip that cycle right there. It's very common. And if the sensor is an active low, means that the output of that sensor is going to be 5 volts until a car is there, and then the sensor goes low. So you want to turn on the light when that sensor is low. It's an active low. In other words, a 0 means something's happening. You push a button, and the button will quite often take that. And a quick example of that, I just give you a simple little circuit here, right there, that pin right here. A very simple little circuit right here, where here's our 5 volts, here's the resistor right here, here's ground, here's our push button right there, and this is our input to our microprocessor, or microcontroller right there. When you push that button, you take that point to ground. If you leave the button unpushed, you're going to read 5 volts there. So in this particular case, this is an active low button right there. And active lows are more common because how much current is this drawing when that button's not pressed? None. It's an open circuit. But if I took the same circuit and I drew it this way, right here, and I push the button on that side there, this is now, and here's my going into my microcontroller there, or microprocessor. There, when I push the button, I open the circuit. This would give me an active high out signal right there. This is active low right there. When I push the button or close the sensor, I take the input voltage of the transistor from 5 volts to 0 volts. This one here is active high. I push the button, I take the input from the microcontroller from, excuse me, when I push this button, I take it high. It's 0 normally. With the button closed, this is a short circuit to ground, and I'm measuring ground right there. So this is actually preferable. In other words, you would want to use this because this here has current flowing right here, right there, all the time until you close that button circuit right there. So this is actually dissipating electricity, drawing battery power, heating up the resistor, doing that when the button's not pressed. When I press the button, I open the circuit, and then there's no current flow. This one here on the top, there is no current flow until I press the button. Now again, a little bit of logic. If you have a switch that is going to be closed most of the time, you might want to use this one right here. A button that's going to be pressed most of the time, then you may want to use the other one, that there. Now, as far as output goes, right there, we typically prefer to have active low outputs because we supply the ground right there, and we'll see that there. In other words, what we have, and we'll talk in more detail about open drain versus push-pull outputs right there. And open drain is almost always going to be an active low output. That's there. So the microcontroller or processor supplies the ground right there. If you go the other way, it's got to supply the voltage to drive the LED or the motor or whatever it's going to do. And these processors don't like to supply a lot of current, so we typically use active low outputs most of the time. So in the microprocessor, microcontroller world, you will see us use active low more than active high. And as I said, I don't know if that was covered in your basic digital course. That's there. Okay, this should be very simple review. And we're going to spend the rest of this hour just reviewing these things. We have what's called an AND gate. It looks like multiplication the way that you normally show it. Right there. That shows a dot in between. The dot may be left off right there. But the output of that is high or active. We're going to say high. It's easier to use the word high that there than keep going back. We'll come back to that active high and active low later, but for the rest of this hour, we're just going to talk about just high and low right there. So if A and B, and the word and is there, if A and B are both high, then the output is high. It's very simple, that there. And a little bit of a background, Boolean algebra has been around since about the 1840s, and I could be wrong. It could be the 1740s. I could be plus or minus 100 years on this date right there. But Boolean algebra was developed by a philosopher in solving logic, philosophical and religious type discussions in Europe. And his name was George Boole, and Boolean algebra was based on his way of solving logic problems. It just happens to work really good for digital electronics. So, but it's not Boolean algebra is not a mathematical formula. It was not developed by a mathematician. It was developed by a philosopher to solve philosophical questions. And of course, some of those things, if you ever took you don't take a course in philosophy. I don't think I saw in your program. I took a few when I was an undergraduate, and they're interesting, but sometimes spending 4 hours writing a paper on why the sky is blue or something is quite interesting. But philosophical courses in philosophy get to be quite interesting right there. So now I did take a philosophy course that was very interesting. It was called critical thinking right there. That's also in the philosophy department. But that's where Boolean algebra comes from. So it wasn't new to digital electronics But the AND gate is just simply you have a truth table. We'll be looking at these truth tables quite a bit from time to time. Right here, this is our truth table. When all else fails, we refer back to the truth table. Then the next one is the OR gate. The OR gate is the output is true if A or B is true, right there. So, is there somebody home? Well, if the husband is home or the wife is home, there's somebody home, right? That's there. But is everybody home? No, the husband and the wife and the children all have to be there for everybody to be home. So it's kind of that type of thing, that the OR, any one, and this shows this is only two inputs or two inputs. These OR gates and these AND gates can have up to 16 inputs right there, or more. We'll look at, if you looked at, did they get into programmable array logic in your basic digital class? Anybody, does the term PAL mean anything? Nope. I didn't think, looking at the syllabus, I didn't think that they got the programmable logic that's there. So, but programmable logic, the way it's laid out, you may have 75 inputs on an OR gate right there. And there's other ways of doing OR gates. This is not a digital course, so we won't spend a lot of time on that there. All right, something that is very important to this class, it was probably not discussed very much in, and actually this is kind of an interesting thing there, that slide is messed up. And the reason that slide is messed up, this says tri-state buffer, that's actually a NOT gate, or an inverter. There is another symbol that is a tri-state buffer, and it looks like this. Right there. And then it has a input right here. Right there. So a tri-state buffer, since the slide is there and the slide is messed up, and as I mentioned before, I stole the slides, so I can't take credit for messing them up, but I could take credit for not reviewing them until right now. This simply says that when we say tri-state, the output is either a 0, a 1, which is 0 volts or 5 volts, or a high impedance, Z. And a high impedance means that it's basically disconnected from the bus. In microprocessor circuits, we have to use a lot of tri-state buffers. They're used quite a bit, especially when we start looking at memory devices. Because memory devices will have an input called output enable. And that what the goal of the output enable does, and it's called different things from different manufacturers. We won't get into that today, but that output has to be active. Or there's another pin also called a chip select. Those are actually usually active low pins and that means that the output is going to be a high impedance. And the reason is in microprocessor systems, it's very, very common to connect multiple devices to the same wire. right there. As we start looking at these circuits there, and we'll spend quite a bit of time. We'll probably use 8086 examples when we start looking at the circuits, because their things are external to the processor. With our processor, things are internal, so I will be looking at it there. But you have, for example, 5 different memory chips. They're all tied to the same memory or data bus. The data bus is the highway, and we'll get to that toward the end of today's class, that contains information that's being passed back and forth. Only one device can put data on that data bus at a time. If 2 devices try to do that, it will usually cause things to malfunction, chips to burn up, bad things happen. So you have to design the system in such a way that only one chip can write to the data bus at a time. Right there. The address bus is a little different, because usually the only device that talks to the address bus is the microprocessor. But the data bus can be talked to by, things such as A to D converters will talk to the data bus. They'll put data on there. Memory chips will talk to the data bus. Other computers connected to it will talk to the data bus. The microprocessor itself will talk to the data bus. Connecting to, graphics cards or displays talk to the data bus. All kinds of devices will talk to the data bus. Only one can talk to the data bus at a time. And the device we use for that is usually a tri-state buffer within up there. Now, we normally don't use tri-state buffers by themselves. They're usually built into the chips that we use. But you'll see a lot of chips that will have a high impedance output. The high impedance output means that there's a tri-state buffer there. If this line here, let me grab I found this finally. If this line is active, then whatever is here is transmitted to the output. Right there. This here, now if you see it without this little thing underneath here, that's just a buffer. And it has absolutely no bearing on the logic of your circuit. It has absolutely no bearing. The only thing the buffer does is that, there's 2 reasons for a buffer. One reason is to prevent current flow. In other words, keep from drawing. I may have the processor on this end, and I may have 5 or 6 devices connected to this wire on the other end. And if they're all drawing current, I don't want to burn up the microprocessor. So the buffer actually amplifies the current. It's like a current amplifier. The other time you might use a tri-state buffer is if you have a combinational logic circuit that you can't afford to have timing glitches. That's there. If you had a basic course of basic digital, you didn't get into timing glitches, I'm sure at all, did you? But a timing glitch is when you have 6 or 7 inputs to a circuit. They all change they all change, and the output changes. But because the number of gates that the various signals go through are not equal, you get an erroneous output before you get the correct output. And that's called a glitch. That's there. And sometimes you'll put buffers in the circuits in order to prevent glitches. Right there. So, and I've worked on circuits where these timing glitches created huge problems. Huge problems. Because you designed them with a certain technology, probably a 74XX family, and then you change the design to a 74HC family, which is a faster family, so it can react quicker to changes. So what happens is that these glitches get picked up by the new system. All we did was, and I've seen this happen multiple times where you had a design, it's worked for 10 years, the customer's happy with it, the manufacturer quits selling that particular speed grade of chips. You have to go to the next faster set of chips. All of a sudden the thing quits working again. It starts having malfunctions. And the problem is you get these timing glitches start popping up right there. And in worst cases, you have to go back and totally redesign the circuit right there. So sometimes you'll find a buffer used just to put in timing delays in order to prevent these glitch problems right there. but most of the time it's for current amplification. This circuit here is a NOT gate, or an inverter. And the only difference between an inverter and a buffer is this little bubble right there. That little bubble at the end there. And you'll see that bubble when we look at the pinouts for the 8086, for example, and we will look a little bit at the 8086 in terms of the hardware discussion there. You'll see the little bubble quite often on pins right there. You'll see a device right here. Here's a device, and you'll see a bubble here, and you'll see an input, and this will be labeled chip select NOT, or chip enable NOT right there. Usually it's chip enable or chip select NOT right there, and you see that little line above that. But when you see this bubble here, that means that it's active low right there. That's what that bubble means when you see that little bubble right there. So that little bubble tells you that input is an active low. So this particular chip, it's a chip select with a NOT with a little bar across it, so it's chip select NOT. If you look at the schematic for the chip, you'll see the little bubble there. Sometimes some manufacturers, and I said the other day that this class is hard because the rules change a lot. This is not a pure science. Some manufacturers don't like to use bubbles. They like to use little triangles like that. That is equal to a bubble right there. But you'll see a little line between here and here. It's, and it all has to do with the CAD software that the company's person is using on how it does that. Cadence does it one way, OrCAD does it another way, ZCAD does it another way, BSCAD does it another way. I'm making some of these names up that there. OrCAD exists and Cadence exists, but BSCAD and ZCAD, and those are ones that I make up. I think there is one called ZCAD though. But again, they show these symbols a little bit different. But those are the two standards that indicate active low inputs right there. And you may see them on outputs right there. If you look at a decoder, and I know that you looked at, say, for example, a 3 to 8 decoder in your basic digital course, that there. A 3 to 8 decoder there's 3 inputs going into it, and one of the 8 outputs is going to be low, the rest are going to be high. That particular chip we're going to be looking at quite a bit later on because that's used for a memory address decoder. That's why it's a 3 to 8 decoder. But if you look at that particular chip right there, you will see it looks like this here, and you'll have A, B, C right here, and then you'll have 8 outputs that look like this right here. Right there. That's what that is right there. And then you may also have a chip select NOT line here with a bubble there. But you should have seen this chip in your basic digital course. If not, we'll cover it up there because we will be using this chip out there. It's a very common chip. I think it's a 74138. It's common enough that I can remember the part number right there. So as we look at right there, and going back to it right there. Okay, so all right, that's kind of a side note from these slides where we talk about the tri-state, the buffer and this active low, but it does pertain to what we're going to be looking at. And as I said, the reason for this is review. And I can tell when I mention a few of these things that they weren't covered in your basic digital class, so I'm not wasting my time right there. All right, the XOR gate is a little bit different. I think I missed a slide there. The XOR gate is kind of a funky thing. It's active only if one or the other is home. Right there. If both parents are home, the output's going to be low. If neither parents are home, it's going to be low. Can I watch TV? If mom and dad are both home, one of them's going to be watching the TV. But if one's home, they're off doing their own thing. So you can only watch TV. But if both of them are home, they lock the TV box so that you don't watch, blue films or something. Out there. Well, in Malaysia they don't have that. In the U.S. we have a channel called HBO and Showtime that show pretty much things that would be that there. So if you have children in your house, you have to lock the TV down some way. There. Back when I had kids, there's a little remote control where you had to know a 3-digit code in order to watch certain channels. That's there. So, but again, the whole idea is if A and B are both low, the output is low. If A is low and B is high, the output is high. If A is high and B is low, the output is high. And if A and B are both high, then the output is low. It's a little different. This chip actually has a lot of use in adders, because if we look at a carry, for example, if we want to add, a single bit, a half adder with that there. 0 plus 0 is equal to 0, right? 1 plus 0 is equal to 1. 0 plus 1 is equal to 1, right? 1 plus 1 is equal to 0 with a carry out. So when you look at adders, the XOR is a very common, because when you add two binary numbers, just looking at one bit, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 0 with a carry out. Right there. So if you were to look at a very simple adder, the simplest circuit for that right there is we've got A coming in, B coming in. If we go through a half adder, this is the symbol for the XOR right there, right there. If we go into here, there's my sum out, and then we go through an AND gate right here, there's my carry out right there. That's a very simple adder right there. This will add that there. Now if you want to go to a full adder, it has to take into account the carry. Right there, that's simple. But this is a very simple circuit. But if I don't have the XOR, the circuit gets much more complicated. Right there. So the XOR is a very, very powerful gate. It's used for a lot of things. And I just showed you for if you want to do adding. XORs are used, for example, two-way switches. This room doesn't have a two-way switch, but if you walk into a large room, you may have a switch at this door and a switch at this door. You walk in and the room's light is off. You want to be able to switch this one on, but then I want to go out, I switch this one back off. That's there. And then when I come in, the next time I come in this one, I want to switch this one. If I put two switches together, then they both have to be switched on. If they're set up as an AND or an OR gate, either switch is on, so I got to turn this switch off, then go over and turn that switch off. But if I do it as an XOR, it works as a two-way switch. That's there. Very common. Back in the U.S., I had a large living room that had multiple entrances, and you would want to use and they call it a three-way switch. And I don't know. I don't think they're very common here. Has anybody seen these kind of switches I'm talking about? That they're not common here. They're very common, like I said, in the U.S. That anytime you have two doors that go into a room, that you would put a two-way switch. Or if you have a light, say, in the staircase, you would have a switch at the bottom of the stairs and a switch at the top of the stairs. Right there. Because if you want to turn on the light to walk up the stairs, you don't want to turn it on and go up the stairs and then have to come back downstairs to turn it off. You'd want another switch at the top of the stairs to turn it back off. So there's multiple uses for that. But as I said, I have not seen them too much here, because even in a classroom like here, where you would normally have switches at front and back with two doors, I don't see them. So you're right, I've not seen it. But that actually is an XOR function right there. So there's lots of practical examples. Like I said, the three-way switch is one, but like I said, I've just not seen it too often. Right there. The NAND gate and the NOR gate are basically an AND gate and an OR gate with a bubble at the end of each of those right there. Now, as it turns out, and without going through everything there is to do to get to that point, there is a philosophy, there's a rule in digital electronics called the universality of NAND gates and NOR gates. And what that basic rule says, in a nutshell, is that I can take any function, any digital function, and I can do it with nothing but NOR gates or nothing but NAND gates. I don't need AND gates, I don't need OR gates, I don't need XOR gates, I don't need inverters. I can do everything with just NAND gates or just NOR gates, one or the other. And that's a very important principle, not in this class, but in an advanced digital course that I've taught in the past, and I've used this technology a lot. There's devices out there called gate arrays. And people will say gate array, but as the drink in the U.S. is called Gatorade. That's there. In Gatorade, the drink actually is named after the Florida Gators, a football team, right there. But a gate array is a sea of gates put on a piece of silicon. It's 5 million, 10 million NAND gates on one little piece of silicon the size of your fingernail, right there. And then you can connect those up to do any type of function you want. And you can build inverters with it. You can do flip-flops. You can do memory devices. You can do everything with that there. And there's an entire series of devices out there that are based on gate arrays that there. And then there's also what's called field programmable gate arrays that are field programmable. And the reason I'm spending a little bit of time talking about that is that is a competing technology with microcontrollers. That's there. So I've done projects where we sat there and we discussed multiple times, is this better to do with a gate array or is this better to do with a microcontroller? That's there. And sometimes we did it both ways, and then we just looked at the results and decided which one to use. Right there. So it is, and a gate array is not, most of them are made out of NAND gates, but they can be made out of NOR gates. That's there. But it's there. So you've got this whole other branch of electrical engineering, or electronics engineering. I've got to be careful here in Malaysia. You separate electronics engineering, electrical engineering. Most countries, the Western countries, everybody's an electrical engineer, whether you're in electronics or whether you're in power. You're all electrical engineers. We don't have electronics engineering. It's all electrical engineering. But regardless, that's an entire different field, and it's very, very popular in many cases. There's a company called Altera that makes field programmable gate arrays. There's a company called Xilinx that also makes them, and Atmel makes them. A lot of the companies out there, and they are so powerful today that you can actually put a microprocessor or microcontroller inside the gate array. You can take an ARM processor and stick it within a Altera gate array, right there, and then put everything else around it. And you'll hear this terminology, system on a chip. Has anybody heard that terminology before? It's called SoC, system on a chip. And what it is a chip that has digital logic on it in the form of a gate array, along with a microprocessor core built into it, or multiple microprocessors, right there. So you've got the system on a chip, and a lot of actually when we look at our 8051 microcontroller that we're using, it's a system on a chip essentially, because it's a 8051 core with lots of stuff put around it. That's there, and it's done as a gate array, right there. So, okay, these are some basic logic circuits. I just did this one right here. This is our basic half adder right there, and you can see the same circuit if we did it without the XOR right there. You can see that we went from 4 gates down to 2 gates. so the XOR saves some time. The full adder they don't even show here going through here, but again you can see that that's now 5 gates to do a full adder right there. This is a design technique, and in a basic digital course I make people do this right there. This basically this is a 4-bit adder, and in each side one of these boxes is the circuit right here, right there. So the design software I use for my digital courses, you can actually draw this circuit, save it as a block, and then put it in the circuit. As a matter of fact, that's exactly what this author did, because I recognized the drawing because it comes out of the Altera Cortex software right there. So this is just a design right there. Right there. Okay, and I'm going the wrong way. Right there. Okay, I mentioned, we'll talk a little bit about decoders. A decoder is basically, you're looking for a particular input. Right here. You're looking for a particular input. This is a 4-input AND gate, but I got inverters on these two. So for the output to be high, this has to be a 1, this has to be a 0, and a 1. Then I will get a 1 out. Any other input will not give me a 1 out. I have to have 1, 0, 0, 1. Just like this one here. 1, 0, 1, 0. Right there. That is looking for the number 5. Right there. Now, this will be a final exam question later on, because I will be tying this up with, in terms of memory decoding and what we would have to design a memory decoder for certain addresses to place memory chips. So we use these decoders a great deal. They're used a lot. Now, again, typically we don't use them with just a single NAND gate, but we could use them with a single NAND gate right there. Usually when we look at the chip, this is actually built into our address decoders or our memory devices. We can use some of those for the decoder right there. But again, we look at, again, I mentioned the 3 to 8 decoder right there. You know, I mentioned that earlier a few minutes ago, where we have 3 inputs right there. Now these here, if they were actual address decoders, they would have a bubble here, because it's pretty much universal with address decoding that you have a active low, and we haven't looked at right there. Okay, everyone's favorite tiny little circuit right here. This is a typical D flip-flop right there, and this actually it's a clock flip-flop right there. Now this is not actually a clock flip-flop because it does an edge trigger. We'll talk, and I don't know how important it is for this class, but in digital there's a difference between a gated flip-flop and a clock flip-flop. A clock flip-flop will only transition on a rising or trailing edge of the clock. This one here transitions at any point. It doesn't, that's there. So, but we're assuming that we don't change between clock cycles. That there. But since they put the little there, that means that's a clocked input. That we're using this as a clocked input right there. So, right there. And all this basically says is that whenever the clock rises, right there, on a rising clock edge, whatever is on D is then just moved out. And it stays there until the next clock edge, right there. So, if you see this here, this diamond here with a bubble, that means that it's going to transition on the trailing clock edge. This means that it transitions here. This one here means that it transitions here. So the bubble means that it's on the falling edge, no bubble, leading edge. Right there. So that bubble comes back into play there. They use that bubble. So, and if you see this diamond, that means it's a clocked input right there. So, and I'm just using these slides to just kind of review doing that there. Okay, getting into some terminology. We use some of these here. You've heard a lot of these before. A bit is either a 0 or 1. It's a single piece of binary data. A byte is 8 bits, right there. And that was the first commercial microprocessor, was an 8-bit microprocessor. So that was the most common. We still use the byte in terms of specifying size of hard drives and memories. And that's there, even though we don't have 8-bit data anymore. Now our microcontroller uses 8-bit, but the ARM processors are using 16 and 32-bit, depending on which model of the ARM processors. That there, the Pixel are either 8 or 16 bits. But anything that Intel is putting out now is a 64-bit processor, and same thing with AMD. Microcomputers are all using 64 bits right there. So, but that there. A nibble is half of a byte, right there. So a nibble is, again, the key thing about a nibble is that it's also 1 hex digit, right there. Now I don't know what happened. They went from bit to a byte to a nibble. When you look at size, you take a little bit, then you take a nibble, and then you take a big byte. So they changed it to word instead of gulp for the next one. That's there. And then you've got double words, and you got quad words right there. So a double word is a 32-bit word. A quad word is a 64-bit. So this slide doesn't give that there. We will work with anything beyond a byte. We might use word on a couple of cases, but typically byte's the only thing we're out there, because we're using an 8-bit microcontroller with that there. I was saying some of the other microprocessors. Now, this is kind of a confusing situation right here. Is that when we look at memory sizes, this is IBM PCs and compatibles. That tells you how old these slides are. IBM hasn't made a desktop computer in 30 years, I think, something like that. They left the desktop computer industry somewhere in the 90s, so it might be like 20, 25 years since they made a desktop computer. That's there, because they made the original IBM PC. It was extremely popular. They got very, very rich. They decided they were going to design it, make something better. They completely changed it. The world took one look at it and said, no, we want any part of it. And they went back. That division closed down, and they didn't make computers anymore. I think they make some laptops now. Because they sold off their microcomputer division. Lavino, I think, bought it out. They sold that off. But regardless, you'll hear the word kilobytes. That's 2 to the 10th. A kilobyte is actually 1024. It's not 1,000. And that's the other thing that makes the digital world different, is because when you talk about kilometers, you're talking 1,000 meters, right? When you talk about kilobyte, you're not talking 1,000 bytes, you're talking 1,024 bytes, right there. So it's a little bit different. That there, a megabyte is 2 to the 20th, a gigabyte is 2 to the 30th, a terabyte is 2 to the 40th. So far, we're only up to the terabytes, but before long, we'll probably get to the next level, which I think is a petabyte. I think is the next level right there. So, at there. And back in the early days, we used to talk about memory sizes in K. My first computer that I bought was a Commodore. It was a V20 Commodore, because there was a Commodore 64 and there was a Commodore V20, and it had 4K of RAM. 4K. Right there. Your phone has how much in RAM? 2 gig. I've got the Samsung. It's got 3 gig. Most of the Apples, I think, have 1 gig. That's there. But you're talking in terms of gig. That there. I'm talking about, and this wasn't a phone. This was a computer right there. My first IBM PC that I bought when I first graduated from college, I could actually afford to buy a real computer. It was a big, it said IBM. They were the only ones that made the desktop computers then, besides the Apples. Your choices were at the Apple II Plus, or the IBM PC. Those were the only two choices. It was over $3,000 US. So I borrowed money. I financed my computer like you would a car, because it cost as much as a car. Because this was 1983, I think it was, or something like that. 84. So it cost, you could buy a car at that point for like $5,000, brand new car. We're talking US dollars here. So my computer was $3,000 US for this computer. It had a green monitor, no color. It had one floppy drive, no hard drives, and I had 64K of RAM. That's there. So you can see where computers have gone since then. I used to work with a guy. He was a full professor, Purdue University. But, he'd been there probably when he retired. He had probably right around 30 years, about what I had when I retired from there. There he might have had a little bit more. And he, at the time I bought that computer, he was asking me, why did I buy so much memory? Nobody could ever write a program so large that it needed 64K of memory. There was a belief system that you would never use that much memory. It was impossible to write a program that large. That's there. So as time has moved along, we went from kilobytes to megabytes. The first hard drive I bought for my same computer, I kept that computer for a number of years. Hard drives came down and they were actually affordable, and I could buy a 10 megabyte hard drive for about $200. Out there, so you can see that there. And then of course gigabytes came along. That there, we started using gigabytes for everything. I worked for Magnavox at one point early in my career, and we were working on a project where we had to collect a lot of data from manufacturing for generating reports for the Navy. So we had a lot of quality control stations in the factory that were networked and tied into our mini computer. We had a little mini computer, and we needed a gigabyte hard drive for that computer. This was in probably 85 or 86, somewhere in that area there. And that particular computer cost us $30,000 US. Was the size of a typical washing machine. That there. When you start putting these things in perspective, you realize that how much like the computer industry has changed in the last 30 years. I've been blessed with the fact that I've watched the changes over the years. I can actually that there. The word terabyte didn't even come into anybody's vocabulary for hard drives. That wasn't even dreamed of until the last 5 to 10 years. That's there. And, I bought my first 1 terabyte hard drive probably 4 or 5 years ago for my desktop computer. That's there. Now they're making 6 terabyte drives, I think is the largest one I've seen. Actually, someone just released, I read last night, a 6 terabyte solid state drive that's 2.5 inches. Will fit into a laptop. 6 terabytes. That's there. So, that's there. And it won't be long before we start blowing the terabyte. We'll go on to the next level. There's a rule in digital electronics and computers. It's called Moore's Law. This is not going to be on the final, but has anybody ever heard of what Moore's Law is? Okay. Gordon Moore was one of the co-founders of Intel back in the 1960s. And he predicted that the number of transistors on a digital IC would double every 5 years. He said that in the 1960s. That law is still in, he was 100% right. That is held true. And they're saying that it's probably going to hold true for the next 5 to 10 years, and then we've reached the physical limits right there. So when you look at that, a microprocessor that had 10,000 transistors in 1960 1975, for example, well, yeah, we'll say 1975 would have 20,080, then 40,000. Now we're talking millions of transistors on a single microprocessor. Now the processors themselves have actually gotten larger, but not that much larger. What's gotten larger is the packaging because of the number of pins right there. So we get into this whole discussion, and like I said, I've sidetracked a few places here. Okay, now we get into inside the computer. This is the key thing. This is what we're all here about. We're looking at microprocessors. That's there. And these slides are actually talking more about desktops, but it also applies to microcontrollers. We haven't differentiated. We've got multiple parts. One is the central processing unit. That is a digital circuit that does the adding, subtracting, multiplying, dividing, moving things around. It's the core part of the microprocessor. Now, when you look at a desktop computer, that's the CPU. They call it the CPU. If you ever want to get an old-time computer geek mad, refer to this box as the CPU. And I know people do it all the time, right? This is my CPU. No, this is not my CPU. That's my computer. It contains everything. The CPU is one IC on the motherboard inside that chip, or inside that box. It's one IC, an integrated circuit in there. That's the central processing unit. We have some input and output devices. When we look at our desktop computer, here's an input device, here's an input device, here's an output device. A printer would be an output device right there. So we have that there. We have two types of memory right here. One is called, and I hate these names, we'll get into more, that there. RAM is random access memory. This is the memory that the computer uses to operate your programs, and it can be changed all the time. ROM is read-only memory. Now, read-only memory also can contain programs. It usually doesn't contain data because you can't change it on the fly. Now, the mix between ROM and RAM is one of the key differences between a microcontroller and a microprocessor system. Most microcomputer systems, desktop computers, have very little ROM. Very little ROM. You probably, if I was talking to a group of people that have played around with desktop computers, that you know what I mean by the BIOS, the basic input-output system for a computer. You hit the delete key when you boot it up. It has the screen on there where you set the priorities for the hard drives and all that stuff. That's there. The BIOS is the startup routine. It's very small. It's one chip on the motherboard. And back in the old days, if you wanted to change the BIOS, you actually had to remove the chip and put a new BIOS chip in. Nowadays, they use what's called flash memory, and you can reprogram the BIOS by downloading a file and running it through a routine upon boot up off of usually a thumb drive or something like that. There's a way of updating the BIOS out there. But the BIOS, or the read-only memory, is very, very small on a desktop computer system. The RAM is where your programs execute. We already talked about the fact that your phone has 2 gig of RAM in it. That's there. So, and RAM is what operates that there. Now a lot of people get RAM and storage mixed. We'll talk about storage in a second. Difference there. But ROM is the startup. That there. Now, when you talk about cell phones and DVD players and TV sets and that they're called read-only memory, which is ROM, but that's a lie today. They still call them ROM, but because they don't use the old-fashioned style, and we'll talk about memory later on in the class, the old type of ROM When you built the chip, the code was in the chip. That there. You bought a 2016 chip from Intel. You had to tell them what you want to put in the 2016. You could buy a 2716, and the 7 means that's erasable. You would put it under an ultraviolet light, and then you put it into an EEPROM programmer, and then you would program it. You could buy another type of chip that you could put into a programmer, and it would burn up resistors inside the chip and program it that way. In other words, it would be programmed. It's a one-time OTP. You'll hear the term OTP, one-time programmable, right there. So there's different types of ROMs. The most common today is actually what they call a flash memory that you can rewrite it multiple times, but it's very slow to rewrite it. And most ROMs today are flash, and they can be overwritten. Out there. And there's the term update your firmware. Anybody know what I mean by update the firmware? You don't hear it? You've never heard that term before? You might have heard it, but you don't know what it means? A software update's different. It's similar. A firmware update is usually something like a DVD player for your house. Some of the early MP3 players, you would do a firmware update. A number of the DVD burners that you put into your computer, you would do firmware updates. And what firmware updates is a DVD player in your home, or Blu-ray player, is a computer-based system. It's got a microprocessor or microcontroller. It's usually a microcontroller that does everything. It's its own computer in its own way. It's a computer system. It's an embedded system. That's there. It has the software to run the DVD player burned into ROM, the flash. So that's what tells the DVD player how to show the menus, where to start, how to set up and play the DVD player. It has to have software to use the DVD player. Right there. Every now and then, if you have, for example, I've got a Sony DVD player right there, and it's a Blu-ray, and it connects to the internet. It doesn't work so well here because it's got the regional coding on it. That there. So, but when I was in the U.S., it allowed me to connect to things like Netflix and Amazon and the various TV shows. It actually had a web browser, allowed me to do things like that with it. But every now and then, I would turn it on, and it was connected to my house internet through Wi-Fi, and it would come back and it would say that it needs to do a firmware update. So it was updating the ROM inside, the software that runs the DVD. Now, when you look at a software update like for Windows, that's just updating the operating system. That's there. When you look at a firmware update, the term firmware means that it's not really software, because you got software, which is just software. You load it off of a disk and run. You upgrade from Windows 8 to Windows 10, you're updating the software. You're updating the operating system. That's there. But if you have, for example, a motherboard that has a BIOS update, you're updating the firmware on the motherboard. It's different. And and you got to be careful when you do firmware updates, because if anything goes wrong during the update, it's a piece of junk from there on out. You've destroyed that there. Some people will do that with their phone. That's there. If you buy, it's not so common here, but they would do what they call root their cell phone. And when I say root your cell phone, means that you remove all the stuff that the manufacturer puts on there, and you go back and run pure Android on it. In other words, you go out there, and there you're updating the firmware. Now, if you do an upgrade, say from Android 4 to Android 5, then that's a firmware update right there. And if you've done that update on your phone, you'll notice that it takes a long time. That's there. So, and firmware, and phones are a little weird, because phones, each version of Android has to be tweaked for each particular model of phone. That's why if you've got phones that run Android, you can't just download Android 5 and update it. You got to wait for the manufacturer to release the update. That there. So, but there are people that get around that and they download it and they run it, but then it loses some of the features of the phone, right there. And it's not recommended unless you really know what you're doing. I don't do it. I'm not that big in the phone. But RAM and ROM are different. ROM is more common in embedded systems. When we look at the software we're going to write in this class, we're going to be using more ROM. Next semester, when you take microcontrollers, pretty much everything is in ROM. A microcontroller might have 64K of ROM and 256 bytes of RAM, and that's enough. That's there. So when we look at that there, it's the other way around there. So, but ROM is considered more permanent. In other words, you don't change it very often. You would do a firmware update on your phone like twice a year, right? That's there. But all your applications get updated. If you got Android, it seems like every day something on my phone's being updated. It's a pain in the neck. If you got Windows, you get updates once a week now. They used to do them all the time on you, but Windows updates frequently. But if you buy a computer with a particular motherboard, you don't update. Most people don't update the firmware on their motherboard ever. I do mine once in a while if I get a piece of hardware that doesn't work right. That's there. So I ran into problems with a lot of the old DVD burners. I'd have to update the firmware on those quite a bit. That's there. So this is kind of a ugly looking. I think I got a better drawing. Yep, that's the first one. This is the one I cleaned up. Okay, this is pretty much the end of today's discussion here. But we're going to be looking at this in much more detail. This is our CPU right here. This is our 8051 or our 8086 or 80, Z80 ARM processor, whatever we want to call this, CPU. There's probably 200 different types of models of CPUs being made today. Atmel makes a bunch of them. Intel, those are the two big players on the desktop. Most of the experts say that the Intel processors are superior over the AMD processors. But the AMDs are a fraction of the price. I personally am using an AMD in my desktop computer. I have a desktop I call Big Bertha that's got one of the larger AMDs. I just couldn't afford to put an Intel Z7 or an i7 in there. But that's the CPU. Then we've got RAM. RAM is our read-write memory. That's the memory that there. RAM is misleading because both ROM and RAM are random access, but RAM is read-write memory. Then we've got our ROM. Then we've got printers, disks, monitors. Now our disk right here, this is storage right here. And a lot of people will confuse when we talk about this here. This is storage right here, and this is what I want to say run memory. In other words, this is what the memory you have to run. It's like the size of the scratch pad, how much memory you've got. Now, putting more memory in a computer will quite often speed it up if you're running applications that require a lot of memory, and the computer, because it runs on a memory, starts using disk space as RAM. And a lot of operating systems will do that. Windows will do that. If you've got a Windows computer with 2 gig of RAM, for example, and you run a program that at times needs 4 gig of RAM, it will steal some disk space and write to it. But writing to the disk is much, 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 much slower than writing the memory. So if you take that computer and you bump it up to 4 gig, that computer all of a sudden gets a lot faster. But there's a point in diminishing returns out there. I find that most people, if you're running engineering type software, you need a minimum of 8 gig of RAM on a computer out there. If you do video editing, 16 gig. I put 32 gig into a computer, and I notice almost no difference in speed between that and 16. That extra 16 gig was just throwing my money in the dustbin. It was a complete waste of money out there, because the computer isn't going to use it. Now, disk space is what stores programs or data files, movies, pictures, documents, software that you want to load, unload. The operating system needs to be loaded in. So this is that there. And this is a generic term. It can mean anything from a flash drive, a hard disk, which is a platinum. Back in my day, that there, we used to not have disk drives. We had tape drives. That there. You ever see the old movies with the great big reel of tape that goes? That was replaced by the disk drive. That there. Those were very slow, very slow. And then I had one computer at one time that actually had a little cassette cartridge I put in. That there. That there. So tapes were common there. Now the disc, they call it disc because that's the most common. Is it's a metal platter that you go through and it writes, and it magnetizes or demagnetizes that there. Now we get to the solid state drives that are basically long-term memory devices, right there. And solid state drives, by the way, is if you don't use them for about a year, they start losing the data on them. They discovered that is you can't program a solid state disk and put it in the shelf as a backup and leave it there. If you do that, then when you need it, you pull it out and you find out that all the data is kind of faded away. That there, it needs to be recharged every now and then. But there, flash drives are a type of solid state drive. There, so we've got the disk drive. Adding more disk space doesn't speed up your computer. It just gives you more room to store more pirated movies. Up there, or whatever you're storing on there. Pictures to upload to Facebook, right there. So I mean, there, and trust me, I record these videos. These videos get quite large, and I need a lot of disk space to edit them there. Like my main computer I use for that, I've probably got a couple terabytes of hard drive space up there, easily up there. Monitors, the word monitor, I've had computers with 2 monitors. I've had computers with 3 monitors. I've settled for 1 monitor now, right there, 1 large monitor. Keyboards, mice, scanners, cameras, the list of input devices go on there. We won't be looking at many, but this is a typical computer setup there. The key thing we're looking at here is we've got the address bus and the data bus. Well, we spend a lot of time talking about that, and that's how we talk between our devices right there. So we look at the address bus here, the data bus, and the control bus. So there are 3 buses there that we have to deal with. The control bus is how we control which direction data is going back and forth, who's writing it, that there. So we're going to spend a lot of our time talking about these interfaces this semester. So, right there. The address bus, right there, it must be assigned an address. Every device in your system has an address. Or, in the case of memory, many addresses, but it's in a range right there. When we look at the address bus, I tend to look at it, for example, your house. Your house has got a house number, but then you live on John 5/C whatever, right? That there. So that happens to be the device where it resides in, that there. And it could be in some neighborhood. I live in, Down Alcota, for example. So you put that's part of that. Then it's in Kuala Lumpur, So you get more and more specific, and then of course you say then Malaysia, that there. So your addresses get you down to the particular location when you look at memory. But we have to decode to get down, because there's many houses that are numbered, 3, for example. But how many houses that are numbered 3 that are on Lorong Curry Dua, right there? Something like that there. So you have to, the number without the street that there. Now how many Lorong Curry Duas are there? Well, there might be one in every other neighborhood there. So then you have to say, well, it's in Dato Karmat. That there. So now I'm down to a particular house. There's only one Lorong Curry Dua in Dato Karmat. There's only one Dato Karmat in Kuala Lumpur. So now I can specifically, if I leave the Kuala Lumpur, there might be a Lorong Curry Dua in Penang. So you have to, same thing with addresses, they have to get down to specific locations. So when we start doing our memory interfacing, we have to set up the addresses properly, right there. The data bus, that's the information we send back and forth, right there. And the control bus is just basically the microprocessor controls. He's playing the traffic cop that's directing traffic, right there. This data is going out. This data is going to an I/O port. This data is going to memory. This data is being a write, so it's going out from the microprocessor. You know, there's a read operation. You send me the data. It's telling me various controls. So I warn you right now, on the final exam, I'm going to be going through the various I/O pins on the 8086, and I will be asking you what the various control lines do. So as I cover those, we'll point those out. Right there. The data bus, the bigger the better. A 64-bit wide data bus contains 8 times as much information at one shot as an 8-bit data bus. Now, that's not 100% true, because that's also a function of the operating system. How many people use Windows 7 here? You use Windows 7. Now, you know that there's 2 versions of Windows 7 out there, right? There's a 32-bit version and a 64-bit version, right? You know the difference between the two. That there. The 64-bit version will use all 64 bits of the data bus. The 32-bit version only uses 32 bits. So if you've got a 32-bit processor, you need the 32-bit version. If you've got a 64-bit processor, you can use either up there. But if you have a 64-bit processor and use the 32-bit version, the 8 bits are closed. It's like the federal highway when they shut off 2 lanes. You know, now all of a sudden you've got traffic jams up there. I have been on the federal highway for years. Back when I lived here before, I used to live at near Bonsar, but you know, up there. And my mother-in-law lived in Subanjaya, so that's the quickest way to get to Subanjaya. Was that, well, I shouldn't say the quickest way, the most direct route, but sometimes that was a large parking lot out there. And the fastest way to make it a large parking lot is close 2 of the 3 lanes, right? So, and that's what you're doing essentially if you're running the 32-bit. Different applications will only use 32-bit, you know, 32-bit instructions. Matter of fact, I'm willing to bet that 90% of the software out there only uses 32 bits. Right there. 90% of the software, they haven't recompiled it to use 64-bit variables. Right there. So, you don't necessarily gain much up there. In microcontrollers, you go from 8-bit to a 16-bit to a 32-bit. You know, it depends on the application. Microcontrollers, you're more price sensitive, so you worry about that. The English is terrible up there. This is a key point here. They're bidirectional. They go one way or the other. Now, the general rule is the larger the data bus, the more powerful the microprocessor. That's a general rule. There are exceptions, but that's a general rule. There are some microprocessors that, and we'll look at that in a little bit more detail, that are 2 sizes. One size internal and one size external. The 8088 is one, for example. We'll look at that in a little more detail. The larger the address bus, the more memory it can address. Right there. So, again, these are there. Now, keep in mind that when you address memory, you're grabbing, if you've got a 32-bit bus, for example, you're going to be grabbing 4 bytes at a time. If you've got a 64-bit bus, you're grabbing 8 bytes at a time. So the address there, the address typically is still at the byte level. But the 8086, for example, has 24 address lines, and it can address 24, or 2 to the 24, or 16 megadata, roughly. You know, the original 8051 had I believe it was a 8-bit address bus. Might have been a 16-bit address bus, I can't remember. But the 8085 had a 16-bit address bus. It could only address 64K. right there. So you get in that there. Now, when you look at some today's processors, I think the i5 can address like 4 terabytes right there of RAM. That's not storage space. 4 terabyte of RAM is a lot of RAM. I haven't seen anybody run applications that large yet. The address bus is unidirectional. The only person that writes to the address bus is the CPU, the microprocessor or microcontroller. That's the only one. The data bus, everybody can write to, and that's why you have to decode and say but only one at a time. And I think I'm kind of wrapping up. We're supposed to end right around up there. This just kind of repeats the same thing I talked about before. Right there. All right. I'm going to kind of leave it go at here because we're going to pick up at registers here. I got a few more. Yeah. A few more slides. I'm going to stop it at this point right here, right there. Because, now we're getting specific into the 8051. So this is our review of everything. And now, next week, we actually start. Now remember, this afternoon I've got a doctor's appointment, so I won't be here. So, plus we're not ready for a lab today anyway. Next Monday, I will be issuing each person a board. You're responsible for turning that in at the end of the semester. I hope I have enough boards. If not, at least we'll draw straws on who's going to share a board. If 2 of you are roommates, then maybe you can share a board. It's typically, in the U.S., to be honest, what I've done is I just made everybody buy their own board. And then typically two people would get together and say, all right, we'll buy one board and share it. I mean, the boards themselves are about, I'm thinking they're right about 100 ringgits. I mean, they're not super expensive. Actually, I think they're cheaper than that. I think they're about somewhere right around 40 ringgits. I think they're right around 40 ringgits is what I paid for these boards. They're very inexpensive. That includes the programmer and everything. So 40 ringgits is very, very inexpensive for these boards. But I bought 20 of them. I suspect a couple of them didn't come back last time, so I may not have quite enough. Hopefully, I've got enough for everybody. That's there. So I've got some other ones that are similar, but that doesn't work. Everyone has to have the same board, or else it won't work. That there. So all right, now this is where I have to. This is what I need here.